I want to thank all the speakers. I want to make sure that Jerry Haber of ARTCOS is online. We have had some difficulties in connecting. Jerry, are you there? Can you confirm? We were having some difficulty in connecting with him. Jerry? There you are. Thank you so much. Jerry, allow me a quick introduction. Is a distinguished scientist and associate director at ARTCOS at Risk and Safety Division. It's my pleasure to introduce Jerry Haber. Your floor is yours. We cannot hear you. Your sound might be muted.
Can you hear me now?
Now is perfect. Perfect. Go ahead. The floor is yours.
Thank you. Is my screen showing?
Jerry, we see your presentation. It's up on the screen.
Very good. Thanks. So I'm going to speak a little bit about the issues of aircraft risk from space lift operations. I will begin with talking about what's happened through the years, how it's evolved, talking about several initiatives that are going on, sponsored in the US by the FAA, both in terms of traditional types of protection approaches, as well as some novel new ways that are being introduced to deal with faster, more responsive, less invasive types of approaches. I began many years ago when I first began to practice flight safety, working with a company that enabled me to participate in evaluating what the risk is to aircraft. In those early days, they had what they called the big sky theory. The idea was that there's just so much space out there within which aircraft fly, so it was highly, highly, highly improbable that we even needed to address the risk to aircraft from failed space vehicles. Moreover, there was the naive approach that should there be a failure, that the fragments would actually encounter the top surfaces of the aircraft. I will show you as we move on that, in fact, given the terminal velocities of fragments in question and the high speed of the aircraft, that it is more effectively useful to think of the aircraft running into the fragments than thinking of them landing on the top surface. So what I want to talk about today is two issues. One, how do we ensure safety of the public as they fly in commercial aircraft and in general aviation? Secondly, we want to take a look at how do we ensure optimal use of airspace by aviation? How do we ensure that the regulations designed to protect the public do not overly restrict the flight of commercial airplanes? So let's begin by taking a look at what some of the issues are with public safety. We need to recognize that both launch and reentry pose risks to both the supporting people and the uninvolved public, on land, at sea, and in the air. The risk comes from hazardous activities, from planned jettisons, and debris from launch failure. We need to think in terms of strategies for closing affected areas of land, sea, and air. And the methodology historically has been to publish NOTAMs, notices to airmen, and to exclude local populations. Why do we have to think about this? Well, here are some examples of what has happened historically, both in the US and in my examples in China, when there has been inadequate adherence to safety precautions. Speaking of an incident in the US, the first slide dates back all the way to 1965. And at that time, there was a Thor launched out of Vandenberg Air Force Base. And the flight safety officer chose to disregard the effects of the winds and noticing how far it was drifting off course. And the consequence was that it indeed failed. A part of the vehicle crashed into a trailer. And fortunately, while there was some damage, the occupants were not injured. They were obviously experiencing the shock. There was a mother on one side of the trailer and an infant on the other side, but no one was injured. In terms of protecting aircraft from malfunctioning boosters, we've got some significant challenges. The traditional approach has to deal with the fact that space launch operations can cause major airspace closures, major in terms of both distance and duration. And we need to ensure that all of this can be managed to continue with adequate safety while controlling the impact on aircraft operations. The contours there show the likelihood of impact of falling debris for a particular mission. This was brought home very forcefully after the Columbia reentry accident in 2003. In this, you can see the impact points from recovered debris. Crisscrossing it, you can see some traces of various commercial aircraft that occurred during the time the debris was falling. As we can see in this, there were some aircraft that crossed once, there were some aircraft that crossed multiple times. We were indeed fortunate that, to the best of our knowledge, no aircraft was damaged and no one was injured. But this highlights the type of problem against which we need to work. So let's talk a little bit about how the safety issues evolved. So in the early days, we thought, well, we have fragment lists for addressing protecting people on the ground. That should be good enough. But then we began to realize that we were missing very small fragments that can be hazardous to aircraft. As is common in analysis and in policy formulation, we went to the other extreme. We ended up defining exclusion regions based on fragments as tiny as 1 gram. That created some real challenges in terms of characterizing it. Plus, it became exceedingly restrictive. We evolved from that to looking at defining a casualty area based on fragment size and the vulnerability of the different portions of the aircraft. In addition, one of the things that got introduced is recognizing that the impact probability distribution with regard to aircraft were not two-dimensional. It's not at just the top surface. It's rather something involving 3 physical dimensions plus the dimension of time. So from this, we evolved to looking at something as a function of aircraft type, and we developed fragment casualty areas as a function of fragment mass. More recently, the efforts have been taken to look and say, well, in those early years, we assumed all aircraft were composed of aluminum, that this material was all we had to be concerned about. Increasingly, we're dealing with composites. Moreover, we've also increasingly had to deal with other damage mechanisms. In addition, there's been some needs to refine fragment characteristics and how they interact with the aircraft. So this is another quick history talking about how this evolved, again, beginning with the debris catalogs based on protecting on the ground, the 1 gram criteria, the evolution to looking at probabilistic aircraft vulnerability models first for commercial jets, business jets, commercial jumbo jets. then the refinements to look at the vulnerability of different components of the aircraft. Supporting this has been some testing by the FAA of the penetrability and damageability of the different components of the aircraft. So at the beginning, I promised to give you the idea of why we're concerned about not using the top surface. The key factors here is if you look at the relative velocity of the debris with respect to the aircraft, it's dominated by the aircraft velocity. And so while it's not true that the aircraft literally comes in on the front surface, that's a much closer approximation to what happens than assuming that it impacts the top surface. In addition, a key factor in doing this evaluation is considering the fact that during the time that the debris can go from the top to clearing the aircraft has advanced. So it's an enhanced volume that's at risk. A second major factor that we had to look at is looking at the relative vulnerabilities of these different components and building in human vulnerability into the evaluations. This chart shows where the casualty area contributions come. This is an example for a 50-gram fragment and for one at 299 grams. Why 299 grams? Currently, a conservative model being employed says that at 300 grams, an impact on an aircraft is catastrophic. And so we're most interested in this intermediate region. One of the things that is in progress right now is refining that 300-gram criteria. We do believe that that's going to be less severe when we finish this work, and there's going to be some chance at 300 grams that it will be catastrophic, and there'll also be some chance of survival, depending on where and the type of aircraft that the impact occurs on. So we're going to talk a little bit about some of the challenges that exist. A major one is the changing materials in aircraft construction. I alluded to that early on in the notion of composites. A second one is the focus has, up until this point, been on penetration mechanisms. We are recognizing there are other types of mechanisms that are important and reevaluating that. And finally, again, major concern in whatever we come up with is limiting the impact of protection on aircraft operations. These next two charts show you how the increased use of composites is something that is of concern. This is something that was published for the 787, and you can see the areas that the different classes of composites are being used in the construction of that aircraft. A historical perspective is shown in this slide. This was obtained from Airbus, and you can see that we started out with very limited use of composites in the 1970 to 1980 timeframe. But as the years pass, the number of places where composites are used has increased. There was a significant concern based on what has happened in studying missile systems that composites fail differently. Indeed, one of the concerns that we dealt with certain types of composites with missiles is given that there is damage, it weakens a system, and you don't just have a puncture, but you tend to have somewhat of an unraveling. We are in the middle of a test program right now to further evaluate damage mechanisms and the vulnerability. So far, the positive news is, in some sense, it's more vulnerable, but in other senses, it's less vulnerable than aluminum. So it's not all bad, challenging news. It is opening up the door to better understanding how vulnerable aircraft are and what we're going to have to do to continue to protect them. So how do we ensure that safety does not unduly impair aircraft operations? Well, we're going to look at two different types of approaches. One, the traditional modeling. As I indicated a little while ago, we've been looking at refining models, and part of that is eliminating excessive conservatism. There's a new concept that has been discussed for many years, but has actually been demonstrated for a few missions, including a aircraft controller simulation with the human in the loop testing to be able to treat debris hazards from failed launches, very similar to the way we treat dangerous flying weather. And I will give you a quick example of the consequence of doing that at the end of this presentation. So there have been two major classes of initiatives that I want to acknowledge. First, the International Association for the Advancement of Space Safety began an initiative that they called ADMIRE. And this was a consortium of international teams, both in Europe and in the US, intending to quantify and manage risks for reentry of space objects, including meteors. So this was going to include both debris from reentry, as well as failed vehicles, as well as meteors coming in. There's a lot of good thinking that went into it. Unfortunately, that did not get funded. In the US, the FAA has been funding some ongoing work, and we've been looking at the fidelity of aircraft materials models, notably focusing on composite materials. We are working on enhancing the fidelity of damage to aircraft and consequence models. And we are developing, as I mentioned, real-time hazard avoidance models that have been demonstrated with people in the loop to be able to adequately protect aircraft by treating things more like the way we treat avoiding weather systems. Finally, as I promised, here's what happens when we try to manage like weather. The orange area shows the exclusion region that was developed using traditional methods for one particular mission. It's over 1,300 miles long, and after liftoff, there is a 46-minute duration during which aircraft may not fly there. The newer concept is much shorter. It's only a little over 250 miles long. And by contrast to the traditional approach, it's only a little over 150 seconds duration after liftoff. So this is where we are going. We're improving things with the traditional approach because this requires the ability to communicate with aircraft, which is not possible currently throughout the world. It is possible in selected regions, as well as focusing on this future concept, which will enable much shorter interruptions. I appreciate the opportunity to present this to you. Thank you.
Jerry, thank you so much. Excellent presentation. All of them excellent presentations. I very much appreciate everyone's time. And this, in essence, concludes our presentations for today. But before we go, I want to again thank the mayor and the municipality for inviting us to be part of this important event, the Portugal Air Summit. And we hope maybe next year we can do some of these presenters from our side in the US to be here in person instead of virtually, and that we could all share some more of these other presentations ongoing at this same time as ours. I believe this was a valuable group of people, and from the feedback I got here with the people in front of me, I think everybody was very happy with the different presentations by everyone. I thank you again for your time and look forward to seeing you all and collaborate with you guys going forward. Thank you so much.